Okay, we've made it to Module 11, and this is going to take a little turn in the course. We're going to be going from physics to astronomy for the remainder of the course. And one thing you may or may not know about me, at least, is that not only do I teach physics, my background is actually in physics, but I am also, I teach the astronomy courses here at ICC as well. I teach the online as well as the traditional. And it turns out that physics and astronomy are very closely related. In a lot of colleges, the Department of Physics is actually a Department of Physics and Astronomy because astronomy uses so much physics. So that's the cool thing, is that you're going to be taking a lot of what you already know and applying it to things that are in space. And it turns out that physics is a really important tool. Without physics, without Newton, we couldn't have put a man on the moon, for example. We wouldn't be able to have various spacecraft interact with comets and land on other planets without the knowledge we gain from physics. So it's a very, very good application of some of the principles that you've already studied. It's very important at the outset to define what we mean by solar system. The solar system, or our solar system, includes everything that is under the gravitational influence of the sun. So, of course, solar means sun. But that, of course, obviously includes the sun. It also includes the planets. And as we'll learn, the planets formed at essentially the same time as the sun did, as well as all the other stuff, big and small, that is gravitationally bound to our sun. All that stuff we include as the solar system. So that's the sun, the planets, and failed planets. Things that never made the grade, never got big enough to become real planets, asteroids, comets, and any kind of debris that is under the influence of the sun and orbits the sun, either close or far away, as it turns out. All that stuff is included in what's called the solar system. Now, when we say solar system, the things that really leap out are the big objects, which include the sun as well as the planets. And it turns out, as we're going to learn a little bit later on in this module, the planets can actually be broken down into two different groups, classified as either inner planets or outer planets. There's 4 inner planets, there's 4 outer planets, and I do recommend that you memorize the order of the planets, know their names, and know the order at which they appear closest to farthest from the sun. In this diagram, you'll see that all the planets are pictured essentially at scale size, obviously not scale distance from the sun, but essentially their sizes are roughly on scale in comparison to the sun. Okay, so the solar nebular theory. I wanted to first address what nebular means. Nebular, you may have heard the term nebulous. It's an adjective. Nebulous is when you refer to somebody's thinking as nebulous, or someone's explanation as being nebulous, that means it's kind of cloudy, it's kind of foggy. It comes from a Latin root for cloud. So the nebular theory, as described on the slide here, is an explanation for how the solar system came to be. The nebular theory says there was a cloud of gas and dust that collapsed and formed the objects we see now in our solar system, the sun, the planets, the asteroids, the comets, all that kind of stuff. Now, how do we know? How was that theory constructed? And how much confidence can we have in that theory? A lot of folks often mistake what the term theory means. Theory is not just a guess. It's not just a wild guess. It's not even an educated guess. In science, a theory has a very specific definition. It is a framework which takes observable data and explains those data. So, for example, the current sizes of the planets, their motions, all that kind of stuff is explained by the solar nebular theory. And some people would say, well, how the heck do we know? No one was around 5 billion years ago. So how would we know that the nebular theory is correct? The important thing about a theory in science is not only does it explain, has explanatory power. So certainly the nebular theory explains why the sun, the planets have the sizes, the motions that they do, but it also has predictive power. What it should be able to do is it should be able to be extended beyond our own solar system. So certainly no one was around 5 billion years ago to see our own solar system form from this cloud of gas and dust. But today we can see clouds of gas and dust in space, astronomers can, and they are indeed seeing those clouds of gas and dust turn into young stars. And those stars have planets around them. And so that's the beauty of the solar nebular theory, is that it has predictive power. And the better a theory is at predicting other stuff, the more confidence we can have in it. Very much like the germ theory of disease. The germ theory of disease, let's say you have an egg salad sandwich, and it's been sitting out on a picnic bench all afternoon in the hot sun. And you go along and you see it and you eat it, and all of a sudden it makes you sick. Well, there's the evidence, or the fact is you got sick. The question is why? And some would say, well, gosh, maybe there's a demon inside you that does not like egg salad and made you throw it up. But there's another theory, the germ theory of disease, is that there are microbes, there's invisible bacteria that grow on egg salad sandwiches when they're left out in the hot sun. And when you ingest those microbes, your body reacts to them and wants to get rid of them by throwing up. The germ theory of disease, if true, would predict that if you do it again, eat that same sandwich, or have somebody else eat that sandwich, and the same thing is going to happen to them. So that's the important thing to understand, is that the term theory should not be dismissed as just a guess, a random guess, an educated guess. A theory in science is an explanatory framework that not only explains facts and data, but can also have predictive power. It's kind of cool to think about our sun. Our sun is the source of all energy here on Earth, even though we get our energy from oil and natural gas and wind and hydroelectric, all that kind of stuff. But ultimately, if you trace back that energy, it all goes back to the sun. Fossil fuels are just, they contain energy from photosynthesis that occurred in plants millions and millions of years ago. But it's the photosynthesis where the energy came from, and that, of course, relied on the sun. That's kind of cool to think about, or hot to think about, I suppose. So how does the sun do it? Well, if you read your book, you probably learned that the sun takes hydrogen. The sun is mostly hydrogen, and through a process called nuclear fusion, turns that hydrogen, actually it turns 4 hydrogen nuclei through a fairly involved process, and I'm not going to go through all the steps, but it takes all those 4 hydrogen nuclei, those are protons, and turns that into one single helium nucleus, which has 2 protons and 2 neutrons. This is different than the nuclear energy we use here on Earth, where we take really massive things and split them apart. In this case, we take very low mass elements and fuse them, smush them together under very high temperatures and high pressures to create this. The thing that's really interesting is that you can think about this as being like a recipe where you've got ingredients. Your ingredients are the hydrogens, and then you've got your result, your product, is the helium. Well, it turns out that the mass of your ingredients there, if you added up all the mass there of those 4 hydrogen protons and compare that to the mass of the helium that you wind up with, there's a difference. Turns out there's a little bit of mass lost, and that was Einstein's huge insight. He realized that mass and energy are actually essentially one and the same, and that mass can be converted into energy, and energy can be converted into mass. So that little bit of missing mass that I just mentioned, remember I said that the hydrogens, when you take all their masses and compare that to the mass of your product, you have a little bit of missing mass. That's what happens in nuclear fusion, is that tiny little bit of mass that's lost, you take that and you multiply it times the speed of light. The speed of light is a huge value, and then square that speed of light. That makes it an even huger number. So you can multiply that tiny little number, the mass, times a huge number, speed of light squared, and you wind up with a fairly large amount of energy. And that's what the sun is doing. And of course, it turns out that the sun is not just doing a small amount of mass. It's got a huge amount of hydrogen to work with. So it turns out that 4.5 tons of mass are converted into energy via Einstein's equation every second. Pretty awesome. So do you know the names of the planets in our solar system? There are 8. And do you know what order they appear, from closest to the sun to farthest from the sun? If you don't, swing by the skill builders and check out the Name the Planets activity. We're going to be getting some more practice about the different planets and their characteristics in the upcoming few slides. My mom, I'd wager, was an English major. She knows her ABCs. She's got a BA, an MA, and PhD from a place called MIT. So when it's help that I am needing with my spelling or my reading, she says, it's no bother. But when I took it for granted that she'd help me with my planets, she said, go ask your father. I was shocked when I discovered that my educated mother could not name the planets. I tried and tried to help her memorize, but she just can't understand it. So I came up with a system that might help her list them. At least that's how I planned it. Cause I was shocked when I discovered that my educated mother could not name the planets. Planet Mercury's closest to the sun, and I tell you, it's a hot little number. A year lasts about a day, and the sun's strong rays can leave you with a pretty bad sunburn. For what it's worth, from Mercury to Earth, just one planet stands between us. Endowed with a shroud of poison gas clouds, the lovely planet Venus. I was shocked when I discovered that my educated mother could not name the planets. I tried and tried to help her memorize, but she just can't understand it. I tried to come up with a system that might help her list them. At least that's how I planned it. Cause I was shocked when I discovered that my educated mother could not name the planets. The fourth rock from the sun is thought by some to be the most similar to ours. The pole's made of ice, it's about half the size of the red planet known as Mars. And a blast from the past made a giant mass of gas. I couldn't write a rhyme much stupider. It looks like a dot, it's got a giant red spot, and we call it the planet Jupiter. I was shocked when I discovered that my educated mother could not name the planets. I tried and tried to help her memorize, but she just can't understand it. I tried to come up with a system that might help her list them. At least that's how I planned it. Cause I was shocked when I discovered that my educated mother could not name the planets. When we reached planet 6, it all started to click, and Mom was picking up the pattern. Who wins the pretty planet prize? It's safe for sore eyes, the ring beauty known as Saturn. And it's me and you, the last two are blue, with atmospheres that could not sustain us. In fact, they're practically twins except for how the one spins, and now you know your Neptune from Uranus. I was shocked when I discovered that my educated mother could not name the planets. I tried and tried to help her memorize, but she just can't understand it. I tried to come up with a system that might help her list them. At least that's how I planned it. Cause I was shocked when I discovered that my educated mother could not name the planets. I was shocked when I discovered that my educated mother could not name the planets. So if you listen to my song, the Very Educated Mother song, you heard the lyrics, planet Mercury is closest to the sun, and I tell you it's a hot little number. A year lasts about a day, and the sun's strong rays can leave you with a pretty bad sunburn. So we kind of get that in this list of characteristics of Mercury. It is the closest to the sun. It also is almost tidally locked to the sun, which means much like our moon always has one side that faces us, same thing with Mercury. It's almost tidally locked to the sun, which means that it doesn't rotate very quickly with respect compared to its orbit. So the time that it takes for it to rotate once on its axis is about 60 days, 60 Earth days. The time it takes to orbit the sun is about 88 days. So notice that one day on Mercury is essentially about 2/3 of a year on Mercury. So therefore it doesn't rotate very, very quickly, which means that the side facing the sun is facing the sun for a long time. And the side facing away from the sun is facing away from the sun for a long time, which is why the daytime is so hot and long, and nighttime is also so cold and long. Because remember that Mercury has no atmosphere. Part of the reason why the Earth is nice to live on is that when we're not facing the sun, when it's nighttime for us, it doesn't get that cold, despite the fact that we're not getting any energy input on our side of the Earth. And part of the reason is because we have an atmosphere, and the atmosphere radiates energy toward the surface of the Earth day and night. But most importantly, at nighttime, that keeps our temperatures relatively moderate. On Mercury, no such moderation because there is no such atmosphere. Okay, continuing with the lyrics to the song. For what it's worth, from Mercury to Earth, just one planet stands between us, endowed with a shroud of poison gas clouds, the lovely planet Venus. Okay, so Venus is the I think it's the Roman god of beauty. Even though it's not that beautiful of a planet, it's easy to spot in the evening or morning sky because it's very, very bright. But if you put a telescope on it, you don't see any details because Venus is enshrouded in this this very, very thick cloud layer of cloud cover. And so you can't see the surface of Venus even with a telescope, because essentially all you're seeing is sunlight being reflected off those cloud tops. So it's endowed with a shroud of poison gas clouds. Its clouds are not made of water or water droplets like the Earth's clouds are. They are made of mostly some really weird stuff, sulfuric acid, all kinds of nasty stuff. So that's why I say poison gas clouds. But it is indeed the next closest planet to the sun. It turns out that Mercury is the closest. It's about 0.4 AUs. AU is an astronomical unit, the distance from the Earth to the sun. So Mercury is about 0.4, 4/10 of the distance from the Earth to the sun. Venus is about 7/10 of the distance from the Earth to the sun. But it is a very, very hot planet because of a runaway greenhouse effect. The fourth rock from the sun is thought by some to be the most similar to ours. With poles made of ice, it's about half the size of the red planet known as Mars. Okay, those are the lyrics to the song. And yeah, it is the red planet. The reason being it's got a lot of iron in its soil. So it appears to be, takes on kind of a reddish hue when viewed through a telescope. It is about half the size of the Earth, and it doesn't have much of an atmosphere. However, and I'm recording this in the fall of 2015, recent NASA research reports they've actually reported liquid water on the surface of Mars. That's very, very exciting. It's very, very exciting for not only the possibility for life on Mars, microbial life, but also with the idea that if humans ever travel to Mars or colonize Mars, you would have a water source, not only for living, but also for perhaps creating fuel. Okay, so now the lyrics go, a blast from the past made a giant mass of gas. I couldn't write a rhyme much stupider. From Earth it looks like a dot, it's got a giant red spot, and we call it the planet Jupiter. Okay, so in the songwriting process, first of all, a blast from the past, that refers to the Big Bang. What is Jupiter made of? Hydrogen. Where did hydrogen come from? Hydrogen came from the Big Bang. So in this case, Jupiter formed along with the rest of the solar system planets about 4.5 billion years ago. The Big Bang about 13.7 billion years ago. So that we're talking distant past, but indeed the lyrics are accurate. A blast from the past made a giant mass of gas. And of course I had to throw in stupider because what else rhymes with Jupiter for a songwriter? From Earth it looks like a dot, which is true. And Jupiter is about 5 AUs away from the sun. The Earth is only 1 AU away from the sun. So even when we're on the same side as Jupiter is, even then we're still about 4 AUs away from Jupiter. That means it's really far away. Now it is a very big planet, but to the naked eye it looks like a dot. Through a telescope it looks like a small disk. But Jupiter is pretty far away. It's got a giant red spot. That spot is a storm. It's actually a hurricane that's been going on for hundreds of years, and we call it the planet Jupiter. Okay, so the lyrics continue. When we reach planet 6, it all started to click and Mom started picking up the pattern. It wins the Pretty Planet prize. It's a sight for sore eyes, the ring beauty known as Saturn. And Saturn easily is the prettiest of the planets. When you look at it through a telescope, you'll see very much like what you see in this image on the slide. A beautiful banded cloud. Those are actually cloud tops we're seeing. There is no real surface to see on Saturn. But you see the bands on the clouds, as well as you see that beautiful ring. So it's easily the most beautiful of the planets. Another interesting thing to note about Saturn is that it is the lowest density of all the planets. It's actually got a density less than 1, which means that it's got a density less than the density of water. And of course, as we learned from back in Module 5, if something is less dense than what it is submerged in, it's going to float. So Saturn, if you had a big enough bathtub, would indeed float in that bathtub. Okay, wrapping up the song. To me and you, the last two are blue with atmospheres that cannot sustain us. In fact, they're practically twins, except for how the one spins, and now you know you're Neptune from Uranus. Well, there's a lot in there, isn't there? The first being, to me and you, the last two are blue. If you check out this slide and the next slide, you're going to see that Uranus and Neptune, or Uranus and Neptune, are almost indistinguishable in the sense that they're almost the same color. Now, why is that? It's because they've got atmospheres that could not sustain us. They've got atmospheres that have a lot of methane in them, and methane tends to absorb the red end of the spectrum and reflect the blue end of the spectrum, and therefore they're illuminated by the sun, just like any other planet. They're not producing their own light, however, they are reflecting sunlight. But the sunlight that's being reflected is mainly the bluish end of the spectrum. The reds tend to get more absorbed by this methane atmosphere. So how can you tell them apart? It has to do with the spin, the way they spin. Uranus is tilted. Essentially, its spin axis is almost parallel to the plane on which it orbits the sun. And so it's actually kind of spinning on its side. Not as we've hopefully seen, the Earth spins on an axis as it goes around the sun on a plane. And it's not straight up and down. It's not perpendicular to its orbital plane, but it's tilted about 23 degrees. For Uranus, it's 98 degrees tilted to the orbital plane. So it is essentially, its axis of spin is essentially parallel to the plane, the plane that is orbiting the sun. Have you ever looked up in the late afternoon or evening sky and seen the moon and kind of wondered, well, what the heck is the moon doing up? I thought the moon was only up during the overnight hours. It turns out that the moon is not always up just during the overnight hours. In fact, sometimes it's not up during the overnight hours. And the reason is that because of moon phases. And moon phases are not due to the shadows of the Earth falling on the moon. It has nothing to do with clouds. These are all bad reasons for explaining the moon phases. Moon phases can be explained by knowing the orientation of the sun, the earth, and the moon. And so if you're not really clear about why there are moon phases, I encourage you to check out the skill builder. Okay, if you check out the diagram or figure 3224 on page 783 of your textbook, you'll get the names for the different phases of the moon. So you should be able to tell, once you've gone through all this material, you should know the difference between a crescent moon and a gibbous moon. It turns out that a crescent moon is when the moon appears to be less than halfway illuminated with respect to our viewpoint here on Earth. When it's halfway illuminated, we call that a quarter moon. We have first and third quarter moons, or last quarter moons. A gibbous moon is when the moon is more than halfway illuminated from our perspective, but not fully illuminated. And that's what a gibbous moon is, and there are waxing and waning gibbous moons. So you should be able to identify the different moon phases just by looking at them. But then you should be able to go beyond that. And in figure 3225, also on page 783, understand why the moon goes from one phase to the next. And also which moon phases are visible at what times of day. And perhaps if you really want to know a lot about the moon, you should be able to understand which direction you would have to be looking and at what time in order to see which moon phase. If you really understand that, if you really understand diagram 3225, you'll understand all those things. That's the cool thing about knowing your moon phases. If you know your moon phase and you can identify it in the sky, you should be able to tell what time it is and in which direction you're pointing at that time.
1, 2, 1, 2, 3 is just a phase, 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 just a phase. Sometimes you're all lit up, sometimes you're blue. It's just a phase, just a phase, just a phase. You're just a little different every time I look at you. It's just a phase, just a phase, just a phase. Some say that you're loony and a little bipolar. Just a phase, just a phase, just a phase. But it's mainly about alignment and illumination solar. Just a phase, just a phase, just a phase. The way it changes unreal, and it's got me kind of feeling like I somehow must be dealing with a cosmic chameleon. It's just a phase, just a phase, just a phase the moon is going through. It's just a phase, just a phase, just a phase the moon is going through. See, the whole thing depends on where you're placed. Just a phase, just a phase, just a phase. When you're between the sun and earth, you don't show your face. It's just a phase, just a phase, just a phase. Past new, you reflect more and more sunlight. It's just a phase, just a phase, just a phase. It's called waxing as you grow bigger from the ride. It's just a phase, just a phase, just a phase. At crescent you're lit, but it's just around the border. When you're halfway lit, we call it first and third quarter. It's just a phase, just a phase, just a phase the moon is going through. It's just a phase, just a phase, just a phase the moon is going through. At gibbous phase, your sunlit face becomes even greater until 2 weeks have passed into a new full moon. You pull the night shift, stay up a little later. You rise at dusk, hang out the whole night through. Past full, you get dark, but there's no sense complaining. Just a phase, just a phase, just a phase. Through gibbous quarter and crescent, it's clear that you're waning. Just a phase, just a phase, just a phase. How I love to watch your phases, it's pretty hypnotic. Just a phase, just a phase, just a phase. 29.5 days, your period sonotic. Just a phase, just a phase, just a phase. Back to your spot ethereal, which some might find material. In 27 days, it's called your period sidereal. It's just a phase, just a phase, just a phase the moon is going through. It's just a phase, just a phase, just a phase the moon is going through.
And if you're still having a hard time understanding the moon phases, have I got a great idea for you. And all you need is a light bulb, a pencil, and a ping pong ball. This activity is actually described in your textbook on page 793, the first 2 think and do questions. And the important thing for this activity is that you create a light source in a corner of the room. So I suggest putting a lamp in your doorway or in a corner. That will act as your only light source for this activity. It will be the sun. Once you have your light in place, put it at the end of in the corner of a room. And what you do is you take your ping pong ball and pencil and you face the light. And you want to put the pencil and ping pong ball at an outstretched arm length. One thing that I advise you to do is to hold the ball a little bit above your line of sight so you don't block the light with your ping pong ball. If you do that, that's an eclipse, and that really doesn't show the moon phases that we're trying to learn. So put it a little bit above, and again, try to shade your eyes for the time being, but see how much of the side of the ball that is facing you is illuminated by the light. Once you've gotten that established, slowly start to rotate yourself counterclockwise as viewed from above. So essentially you'll be turning toward the left. So rotate yourself very slowly, and again, keep an eye on your ping pong ball. See how much of the face that is facing you is illuminated. As you continue to move around, and again, get about a quarter of the way around, take a look at it, see how much of the ball is illuminated, turn all the way around, see how much of the ball is illuminated, and so forth and so on, keeping yourself moving through the different phases until you return back to your original position where the moon, remember the ping pong ball is the moon, is between your sun, which is your light, and the earth, which is you. When I talked about Mercury earlier, I mentioned about the fact that it is almost tidally locked with the sun. Well, the moon is tidally locked with the earth. That means that the gravitational forces of the earth and the moon have caused the moon to essentially have the same face always facing the earth during its orbit around the earth. And that's what we're seeing in this diagram. So I want you to understand that the shadowed part of the moon here, of course the blue is the moon and the yellow circle is the blue is the earth and the yellow circles are the moon. The shadowed part of the moon is not really shadowed. It's just the side that's facing away from the earth. So if we have the moon here, let's say that this dot then would be visible from the earth. And then a week later, notice that as it orbits the earth, it's going in this direction. It's also going to rotate. Notice the direction of rotation. And so it rotates a little way until, notice that that same dot is still facing the earth. And then a week later, we continue around, and it's continued to rotate in the same direction, so that same dot is facing us. And now in the image that's in our foreground, we can't see the dot anymore, but the dot is indeed facing the earth. So notice that the dot, which started out pointing to the left, and then 2 weeks later was pointing to the right, winds up 2 weeks later pointing to the left again. So our moon has done one full spin on its axis in the time that it took it to do one full orbit. And of course, one full orbit of the Earth by the moon, we call that a month. And therefore, a moon day, the time it takes to spin once on its axis, is the same as a moon year, what we call a month, the time it takes to orbit around the Earth. And therefore, it spins on its axis once for every time that it goes around the Earth once. And therefore, the same side of the moon always faces the Earth. Now, if you remember when we did the ping pong ball activity, I told you not to put your ping pong ball in between yourself and your lamp, because that was essentially creating what's called a solar eclipse. When the moon is directly between the sun and the earth, you get a solar eclipse because the shadow of the moon essentially is cast upon a little portion of the earth. So if you're in that little location on the earth, you would see no sun at that point. Even though it's daytime, you're on the sun facing side of the earth, you would not see the sun because the moon would be blocking it out. So you might wonder, well, gosh, why don't we have solar eclipses every month? It turns out that the plane on which the moon orbits the Earth is not the same as the plane that the Earth orbits the sun. They're a little bit off. The moon is about 5 degrees. Its plane is inclined about 5 degrees with respect to the plane of the Earth orbiting the sun. So that means that what we have here is a new moon, because the unilluminated side of the moon is the side that is facing the Earth. And that's what you have to be a new moon phase in order to have a solar eclipse. But most new moon times, the moon is actually, it is between the Earth and the sun, but it's not exactly in a line. It might be up here a little bit. It might be a little bit above the actual line between the Earth and the sun. So therefore, you would still have the shadowed side of the moon facing the Earth, but its shadow being cast off into space, the Earth wouldn't move into that shadow, and therefore you wouldn't have an eclipse. Or it might be down here on a particular month. Again, because the moon's orbit is indeed inclined. So if it was down in this position, then again, it would cast a shadow into space, but the Earth would not move into that shadow, and therefore no eclipse. It would still be a new moon, but it would not be a solar eclipse new moon. Again, think back to when you were using your ping pong ball, and again, I told you to hold the ping pong ball a little bit higher, because if you just held it kind of at chest level, when you spin away from your light, the moon is going to move into your shadow, and therefore you wouldn't technically see the moon, right? The side that would be facing the Earth would be unilluminated. Of course, that's not really what happens. Most months, you do see the moon when it's in that position. When the Earth is between the moon and the sun, quite often you do see the moon. In fact, you see a full moon. And that's because quite often the moon does not move into the Earth's shadow. Most times, again, because of that inclination, the moon actually moves a little, it's a little either above or a little bit below the Earth's shadow zone. And therefore you would see that fully illuminated side of the moon from the nighttime side of the Earth. You would see a full moon. Only when your full moon moves into the Earth's shadow, that's when you would have a lunar eclipse.